Hello and welcome, fellow space explorer. Before we begin, take a slow, steady breath and allow your body to relax into stillness. If you value calm, evidence-based journeys through space and science, consider subscribing. It helps this channel remain a quiet place for thoughtful exploration, guided by real observations and measured facts. Tonight, there is no fiction and no rush. Only what physics, biology, and space missions have carefully recorded beyond Earth's protective atmosphere. Out there, distance changes everything: how the body functions, how time is experienced, how survival is measured. Now, gently turn your attention outward, into the deep silence beyond our world, and let's begin understanding what deep space truly means for the human body. The universe stretches out before you in every direction, a silent expanse that holds distances far beyond ordinary comprehension. You imagine the space surrounding your own planet, where the sun sits at the center of a local gravitational dance with the Earth and other planets. Even within this familiar neighborhood, the distances are immense. Light takes about 8 minutes to travel from the sun to reach your eyes, and you sense how vast that small journey is compared to the distance to any other star. Beyond our sun, stars are scattered across the night sky, each one a glowing point of light, yet the nearest of these, Proxima Centauri, is over 4 light-years away. That means light from this star has traveled more than 23 trillion miles to reach us, a number that is difficult to imagine, yet measured precisely through observation. You let your mind follow the measurements astronomers use to quantify these great distances. Parallax is one of the first methods, where the apparent shift of a star against more distant stars is observed from Earth at different points in its orbit. By carefully measuring the angle of this shift, you can calculate the distance to the star with remarkable accuracy. This method works reliably for stars within a few hundred light-years, and you appreciate the patience and precision required for these observations. Each small angle measured represents enormous distances and emphasizes the scale of the cosmos surrounding your world. As your awareness expands further, you consider stars beyond the reach of parallax. Here, astronomers rely on the properties of light itself. Redshift is one such tool, where the stretching of light waves reveals how distant galaxies move relative to you. The farther a galaxy is, the more its light is shifted toward longer wavelengths. This evidence is collected through powerful telescopes and spectrographs, instruments designed to record the detailed characteristics of light. Each measurement is a careful, repeated process, requiring calibration and cross-checking. The quiet accuracy of these methods allows you to trust the scales you are beginning to visualize. Even closer to home, the space between stars is not empty in a classical sense. It contains thin clouds of gas and dust, particles so sparse that your mind can barely grasp their presence. Yet they contribute to the structure of galaxies. Interstellar space is defined by nearly perfect vacuums, with densities averaging about 1 atom per cubic centimeter. Compared to the air you breathe, this is profoundly empty, and yet, it is precisely this emptiness that lets light travel uninterrupted across the immense void, allowing you to see stars that are hundreds or thousands of light-years away. You sense a quiet stillness in this void, a vast arena measured not in miles or kilometers, but in the time it takes light itself to traverse it. You trace the Milky Way with your imagination, picturing a spiral galaxy about 100,000 light-years across. The Sun is located in one of its spiral arms, approximately 26,000 light-years from the galactic center. As you consider these numbers, it becomes clear that even neighboring stars are comparatively close within the context of the galaxy. Beyond the Milky Way, other galaxies appear as faint, distant smudges of light. Some, like the Andromeda Galaxy, are more than 2 million light-years away. You begin to grasp how each galaxy is an island of stars, separated by distances that challenge even the most patient human imagination. Observational astronomy continues to refine these measurements. Cepheid variable stars, for example, pulse with regular brightness cycles that allow astronomers to determine their intrinsic luminosity. By comparing this intrinsic luminosity to the brightness observed from Earth, you can calculate the distance with impressive precision. Supernovae, particularly type Ia supernovae, provide another reliable measure. They reach consistent peak luminosities, and by observing their light curves, astronomers can extend distance measurements even further into the cosmos. Each method reinforces the other, building a layered, evidence-supported understanding of space that is deeply satisfying in its reliability. As you continue to follow the evidence, your awareness reaches beyond even our galaxy. You think of the Hubble Space Telescope, which has observed galaxies billions of light-years away. The light reaching the telescope today began its journey before the formation of our own solar system. This realization is not just a poetic notion. It is based on careful measurement of the expansion of the universe, calibrated through observations of thousands of galaxies. The universe is dynamic, stretching with time, and each photon traveling toward us carries a history that can be reconstructed through science. You allow your mind to rest in the certainty of these facts, absorbing the immensity of space in a calm, measured way. Even within these immense distances, individual measurements remain precise. You reflect on how astronomers account for factors like interstellar extinction, where dust absorbs and scatters light, or gravitational lensing, where mass bends the path of photons. Each observation is corrected using established physical laws, leaving you confident that what you perceive through science is both accurate and meaningful. You imagine the careful observation logs, the repetitive scanning of regions of sky, and the verification of data across multiple instruments. There is a quiet, methodical rhythm to this work that mirrors the slow, expansive rhythm of the cosmos itself. Your mind lingers on the concept of a light year, a distance defined by the distance light travels in a single year. It is approximately 5.88 trillion miles, a scale that transforms familiar distances into something almost incomprehensible. Even at the speed of the fastest spacecraft humans have built, it would take tens of thousands of years to reach even the nearest stars. The vastness of space is not just a physical measurement. It is a framework for understanding the limits imposed by nature itself. As you absorb this, there is a sense of awe, not emotional but contemplative, rooted in the certainty of measurable reality. In this quiet observation, you begin to see space as a structured, measurable environment. It has depth, scale, and boundaries defined by the laws of physics. Your mind traces the distances between stars, the arrangement of galaxies, and the trajectory of light over cosmic timescales. Each fact rests firmly on observation, calculation, and repeated confirmation. There is no need for embellishment, for the universe's immensity speaks through its numbers and the careful methods used to measure them. You feel a gentle calm as you allow yourself to be fully present within this measured vastness. And as you rest in this understanding, it is natural to notice that while space is vast, it also operates within constraints defined by the behavior of light itself, the speed at which information and matter can move, and the structure of matter and energy. This awareness introduces the quiet realization that the universe's immensity is coupled with boundaries that govern motion, energy, and interaction. You sense the beginnings of the rules that will shape any journey through these distances, inviting your mind to consider the fundamental limits imposed by physics, and the speed at which any traveler could move through this silent, stretching cosmos. You begin by considering motion in the universe, how objects move through space, and how speed is measured relative to one another. In everyday life, you observe motion as changes in position over time, and this intuition works well at the scales of your daily experience. Yet, when you extend this understanding to the cosmos, the rules shift subtly but profoundly. Light travels at a constant speed in a vacuum, approximately 299,792 kilometers per second. This speed is not just very fast. It is the maximum at which any information, energy, or matter can travel according to the laws of physics as described by Einstein's special relativity. You feel a quiet curiosity as you let this fact settle into your mind. You consider why this speed limit exists. It is not arbitrary, but a consequence of the nature of space and time. When an object with mass accelerates toward the speed of light, its relativistic mass increases, making further acceleration require progressively more energy. To reach the speed of light would require infinite energy, which is impossible to provide. You follow this logic slowly, letting your mind understand that the universe itself enforces this limit through fundamental physical laws. There is no barrier to discovery, only a boundary to motion that is consistent and measurable. Experiments repeatedly confirm these principles. Particles accelerated in facilities like the Large Hadron Collider approach nearly the speed of light, and scientists observe measurable increases in mass and the slowing of time for these particles relative to stationary observers. These effects are not theoretical. They are quantifiable and repeatable. Time dilation, for instance, has been observed with precise atomic clocks on airplanes and satellites, confirming that moving clocks run more slowly relative to those at rest. You notice the calm precision in these results, a reflection of the reliability of physical law. Light itself provides a practical example of this limit. Photons, the particles of light, move at this maximum speed naturally because they have no rest mass. Matter, however, always carries mass, which is why no spacecraft, no matter how advanced, can ever fully match the speed of a photon. You imagine a beam of light traveling from a distant star, reaching Earth after years or centuries of journey. The beam's constant speed is a cosmic metronome, regulating how quickly information can cross the vast emptiness. Each photon represents both distance and time, illustrating the immutable nature of the speed limit. Even small velocities approaching this cosmic boundary produce noticeable effects. Time dilation affects astronauts traveling in high-speed orbits, although the differences are tiny on human timescales. Observations of cosmic rays, particles moving close to the speed of light, show pronounced increases in energy and mass. These real phenomena provide concrete evidence of the universal rules governing motion. Your mind absorbs this without strain, appreciating that the limits are not theoretical obstacles but observable, predictable consequences of reality. You reflect on the consequences for interstellar travel. Distances measured in light-years are not just large numbers. They define the minimum travel time given the cosmic speed limit. Even the nearest stars are separated from Earth by years of light travel, making rapid journeys across the galaxy physically impossible. You imagine a spacecraft attempting to reach Proxima Centauri. Even if it could accelerate constantly at the maximum sustainable rate, it could approach but never reach the speed of light. Your mind settles into the calm acceptance that these limits are not negotiable but integral to the structure of space and time. Relativity also introduces an elegant symmetry between space and time. Moving faster affects both the distance experienced and the passage of time for travelers. As your mind considers this, you notice that the universe preserves causality. Effects cannot occur before their causes because information cannot exceed light speed. Observations of distant events, such as supernova explosions, confirm this order, showing that light travels in predictable ways, reaching you in sequence according to distance. This consistent behavior allows astronomers to reconstruct cosmic history accurately, giving your mind both reassurance and a sense of scale. The implications extend to energy requirements as well. As velocity increases, the energy required rises steeply, following relativistic equations. Accelerating to even a fraction of light speed demands exponentially more fuel and energy. You consider advanced propulsion concepts like nuclear fusion drives or theoretical antimatter engines, and recognize that while these technologies might achieve higher speeds than current spacecraft, they still cannot circumvent the light speed limit. The universe sets the ultimate speed, and each calculation reinforces the consistency of this principle. You feel a quiet respect for the precision of these laws. Observationally, light speed limits also define what you can know about distant objects. Information from stars, galaxies, and other cosmic phenomena takes time to reach you, meaning you always observe the past. When you look at the sun, you see it as it was 8 minutes ago. When you observe distant galaxies, you see them as they existed millions or billions of years ago. This slow unfolding of knowledge is not a limitation but a natural consequence of light's constant speed. Your mind finds calm in the certainty that every measurement, every observation, is rooted in immutable physical rules. You also notice that relativistic effects, while significant at extreme velocities, are negligible at everyday speeds. Cars, airplanes, and even interplanetary probes move so slowly relative to light that time dilation and mass increase are effectively zero. This contrast allows you to appreciate the universality of the principle without feeling overwhelmed. It governs the cosmos at large, shaping the behavior of stars, cosmic rays, and spacecraft, while leaving daily life comfortably unaffected. You sense a quiet rhythm in this distinction, a harmony between cosmic limits and familiar experience. Even thought experiments reinforce the impossibility of exceeding light speed. Consider a hypothetical spacecraft accelerating toward light speed. As it approaches this maximum, energy demands increase, onboard clocks slow relative to stationary observers, and relativistic mass rises. Calculations show that no finite amount of fuel or technology can overcome this barrier. These principles are not abstract. They are confirmed repeatedly by observation, particle physics, and astronomical measurement. Your understanding rests on solid evidence, allowing your mind to absorb the enormity of cosmic rules without strain. As your awareness of this limit grows, you see that motion in the universe is tightly bound by predictable, measurable laws. The maximum speed acts as a governing principle, determining how far and how quickly anything can travel. It structures the relationship between space, time, energy, and information. There is no uncertainty in this rule, only clarity and precision. You feel the gentle reassurance that comes from understanding the universe's consistent behavior, a calm certainty that governs even the vastest distances. And as you rest in this understanding, your mind notices that speed limits are closely linked to energy and distance, hinting at the immense challenges any journey through interstellar space must overcome. The very scale of the cosmos interacts with these physical boundaries, setting the stage for questions about how energy, propulsion, and resources must align to make even slow travel across the stars possible. You begin by considering the relationship between motion and energy. Every object in motion carries kinetic energy, which increases with mass and velocity. For everyday objects, this energy is small and easily provided by engines or simple mechanisms. Yet, as velocities approach significant fractions of light speed, the energy required grows rapidly, following the equations of special relativity. Even a modest spacecraft would require enormous amounts of energy to accelerate, far beyond what is used in everyday life. You let your mind adjust to the scale, noticing the quiet precision of these calculations and the predictable consequences they describe. Kinetic energy is determined not just by speed, but also by the mass of the object. You imagine a spacecraft weighing several tons, carrying fuel, life support systems, and scientific instruments. As you calculate the energy needed to accelerate to a fraction of light speed, the numbers expand rapidly. For example, reaching 10% of light speed would require energy comparable to the total annual energy consumption of all humanity. Each additional increment in speed requires increasingly more energy, illustrating the exponential challenge imposed by relativistic physics. The numbers settle in your mind slowly, a steady rhythm of calculation and comprehension. You consider the mass-energy equivalence described by Einstein's famous equation, E equals mc squared. This principle shows that mass itself is a form of energy, and conversely, energy can be converted into mass. In practical terms for propulsion, this equation demonstrates why antimatter or nuclear reactions can theoretically provide much higher energy densities than chemical fuels. Even so, the quantities of antimatter needed for interstellar travel are staggering, and current technology produces only minute amounts. The reality of energy requirements reinforces a calm acceptance that natural limits define the feasibility of interstellar journeys. Chemical propulsion, the most familiar method, is insufficient for these scales. Rockets like those that carry astronauts to the moon rely on chemical reactions, which release relatively small amounts of energy per unit of fuel. You observe that even the most efficient chemical rockets cannot approach the speeds necessary to traverse light years within human timescales. The exponential increase in fuel mass needed to reach higher velocities makes this method impractical for interstellar missions. You sense the inevitability of physical limits, noting that practical engineering cannot bypass fundamental energy constraints. Nuclear propulsion provides greater efficiency. Nuclear fission or fusion releases millions of times more energy per unit of mass than chemical reactions. You imagine a spacecraft powered by controlled nuclear reactions, steadily accelerating over long periods. Even with this energy advantage, achieving significant fractions of light speed would require vast amounts of fuel and an extremely efficient conversion of energy into thrust. The calculations remind you that nature sets stringent boundaries, And while nuclear energy opens possibilities, it does not eliminate the fundamental challenges imposed by distance and velocity. Antimatter propulsion, in theory, offers even higher energy densities. Matter-antimatter annihilation converts mass almost entirely into energy, making it the most potent known source. Yet antimatter is exceptionally rare and difficult to store safely. Even if production scaled up to industrial levels, the quantities required for interstellar travel remain astronomical. You picture the delicate handling, the shielding required, and the sheer precision needed to convert this energy into propulsion. Each consideration reinforces the reality that high energy densities, while impressive, are still constrained by practical limits and safety concerns. You also consider the efficiency of energy transfer. No propulsion system can convert all available energy into motion. Some energy is always lost as heat, radiation, or vibration. This inefficiency compounds the challenge, requiring additional fuel to compensate. Engineers calculate specific impulse to quantify this efficiency, comparing how effectively different propulsion systems convert fuel into thrust. The careful measurement and optimization of energy usage demonstrate the meticulous planning needed for long-duration missions, emphasizing that every joule must be accounted for with precision. Even when using the most advanced theoretical propulsion, the duration of interstellar travel introduces further energy considerations. A spacecraft accelerating continuously over decades must carry fuel not just for initial acceleration, but for deceleration near its destination. The energy requirements double or triple depending on mission profile. You imagine the calculations extending over multiple decades, integrating physics, engineering, and logistics. The sheer scale of energy and planning brings a quiet sense of awe at the complexity required to navigate space safely and efficiently. Your mind then turns to realistic examples. Voyager 1, humanity's fastest probe, travels at about 17 kilometers per second. At this speed, it would take over 70,000 years to reach Proxima Centauri. Increasing this velocity even tenfold requires more than 100 times the energy, highlighting the steep scaling imposed by relativity. You absorb the calm certainty that energy demands define the limits of motion through interstellar space, and that these numbers are grounded in measurable, repeatable physical laws rather than speculation. You consider energy not only for propulsion but also for sustaining life aboard a spacecraft. Life support systems, temperature regulation, and radiation shielding all consume energy. If humans were aboard, food production, water recycling, and oxygen generation would further add to requirements. These needs do not scale linearly with speed. They persist over time, emphasizing the prolonged challenge of maintaining a habitable environment. Your mind rests in the quiet understanding that energy is the fundamental currency of interstellar travel, constraining both motion and survival. Calculations of energy requirements also reveal the importance of mass reduction. Every kilogram of additional mass increases the energy needed for acceleration. Engineers consider lightweight materials, compact designs, and efficient fuel storage to minimize this burden. You imagine the spacecraft as a carefully optimized system, each component chosen to reduce unnecessary mass while maintaining function. This careful balance of energy and mass illustrates the interplay of physics and design, a precise dance governed entirely by natural law. The constraints imposed by energy extend to mission planning. Long journeys require careful timing, potentially waiting for favorable planetary alignments or optimal energy availability. You follow the logic of planning decades or centuries in advance, where each joule and kilogram is accounted for. The calculations are exact and immutable, reflecting the universe's unchanging rules. Your mind settles in the rhythm of these considerations, understanding that energy requirements are not abstract obstacles but precise, predictable limits imposed by the laws of physics. In contemplating energy on cosmic scales, you notice that these requirements are enormous even for modest spacecraft. The vast distances of space, the speed limits imposed by relativity, and the inefficiencies of real-world systems all combine to create a barrier to interstellar travel. These challenges are quantifiable and measurable, not hypothetical, and they provide a clear sense of the scale involved. You feel a quiet wonder at the scope of human ambition when set against the immensity of space and the precision of physical law. And as you absorb the magnitude of energy needed for motion across the stars, your mind begins to sense that propulsion, mass, and energy are only part of the story. The universe presents other obstacles, from environmental hazards to radiation, that will interact with these energy requirements, shaping the possibilities and limits of any journey through interstellar space. You begin by considering the principle of propulsion, the action of generating thrust to move an object through space. In everyday experience, you observe cars, airplanes, and boats using engines or motors to push against the surrounding medium. In the vacuum of space, there is no air to push against, so motion relies on expelling mass in one direction to generate an equal and opposite reaction. This principle, first articulated by Newton, is simple in theory but becomes increasingly complex as you scale up to interstellar distances. You feel the gentle certainty of these laws, knowing that motion is governed by predictable, measurable forces. Chemical rockets are the most familiar method for generating thrust. They combine fuel and oxidizer in controlled reactions, releasing energy that propels the spacecraft. You imagine the fiery exhaust of rockets leaving Earth's atmosphere, carrying probes and astronauts toward orbit. These engines are highly effective for short trips within the solar system, yet the energy they provide is insufficient for interstellar journeys. The amount of fuel required grows exponentially with desired speed, creating a practical limit. You absorb this fact calmly, noting that chemical reactions cannot overcome the immense distances between stars. Ion drives offer a more efficient alternative. By accelerating ions using electric fields, these engines produce small thrust over extended periods. You picture a spacecraft slowly but steadily increasing its velocity, with a stream of ions leaving the engine at high speed. The thrust is tiny compared to chemical rockets, but the fuel efficiency is much higher. Despite this advantage, ion drives still cannot achieve speeds approaching light, and the journey would take tens of thousands of years to reach even the nearest star. You notice the quiet logic. Propulsion efficiency alone cannot overcome the vast scales of space. Nuclear propulsion provides additional possibilities. Fission or fusion reactions release millions of times more energy per unit of mass than chemical reactions. You imagine a spacecraft with a controlled nuclear engine, accelerating over decades with a steady, constant push. Fusion, in particular, could provide sustained thrust with relatively compact fuel, but engineering such a system remains extremely difficult. The challenges include containing the reaction, converting energy into usable thrust, and managing heat dissipation. Each consideration reminds you that even with powerful energy sources, practical engineering constraints are significant. Antimatter engines are often discussed as the ultimate form of propulsion. Matter-antimatter annihilation converts mass almost entirely into energy, providing the highest theoretical energy density known. You imagine the delicate handling and storage of antimatter, where even a tiny failure could release catastrophic energy. Current technology produces only minuscule quantities of antimatter, and storing it safely for years or decades remains beyond reach. Even if production scaled up, the quantities required for interstellar travel are immense. You let your mind rest in the understanding that natural laws govern both energy and mass, setting precise limits for any propulsion system. Light sails offer another approach, using radiation pressure from sunlight or lasers to accelerate a spacecraft. Photons have no mass but carry momentum, which can gradually transfer to a reflective sail. You envision a spacecraft slowly gaining speed as it is pushed by concentrated beams of light. This method avoids carrying fuel, which reduces mass and energy constraints. Yet acceleration is limited, requiring decades to reach significant fractions of light speed. The concept demonstrates creativity within physics, but the timescales remain extremely long. You sense the quiet balance between innovation and natural limits. Each propulsion method must also account for the mass of fuel, payload, and structure. Carrying more fuel increases total mass, which in turn increases the energy needed to accelerate. This feedback loop, called the rocket equation, imposes strict constraints. You picture engineers carefully calculating every kilogram, ensuring that the spacecraft can accelerate efficiently without becoming unmanageable. The mathematics are precise and consistent, reinforcing the understanding that natural laws are exact and immutable. Your mind follows these calculations slowly, resting in the certainty of their predictability. Sustaining acceleration over long periods adds additional complexity. A spacecraft cannot rely on brief bursts of thrust. Continuous or repeated acceleration is required to reach high velocities. This need magnifies fuel consumption, mechanical wear, and energy transfer challenges. You imagine decades of careful operation, with every system monitored and maintained to prevent failure. The vast scale of these operational requirements underscores the difficulty of interstellar travel and the interdependence of energy, propulsion, and engineering. You absorb the quiet logic of these relationships without strain. Environmental factors also influence propulsion. Interstellar space is not perfectly empty. Microscopic particles, cosmic dust, and radiation can impact a spacecraft traveling at high speeds, requiring shielding or active avoidance. Even the smallest particle can cause significant damage at relativistic velocities. You consider the trade-offs between mass, energy, and protection. The universe imposes constraints that are precise and unavoidable, shaping what is feasible and safe. Your awareness rests comfortably in the understanding that every physical law contributes to the overall challenge of moving through space. You reflect on current spacecraft and their capabilities. Voyager 1 and 2, humanity's fastest and most distant probes, travel at tens of kilometers per second. They are successful in exploring the solar system, yet their speeds are minuscule compared to light speed. Increasing velocity even tenfold requires energy increases far beyond what is currently available. These concrete examples demonstrate the gap between achievable motion and the speeds required for interstellar journeys. You sense a quiet acceptance that nature establishes boundaries that no engineering ingenuity can entirely overcome. Considering interstellar missions also brings attention to mission duration. Even with optimal propulsion, travel times span decades, centuries, or longer. Generational spacecraft, designed to sustain life over multiple human generations, have been proposed. You imagine the careful planning required for such missions, where propulsion, energy, and life support must work flawlessly for decades. Each additional system adds mass, which in turn increases energy requirements. The feedback loops are exact and measurable, showing that practical limitations are rooted in physics rather than imagination. You also notice the interplay between propulsion and navigation. Accurate course corrections are essential over light-year distances, requiring precise thrust control. Small deviations can accumulate into large errors over time, meaning propulsion systems must be both powerful and finely tuned. The universe allows no shortcuts, and every adjustment must respect physical laws. You feel the gentle reassurance of this order, recognizing that motion through space is not random but governed by measurable principles. In observing these constraints, you realize that no single propulsion technology solves all challenges. Chemical, nuclear, antimatter, ion, or light sail systems each offer strengths and limitations. Combining approaches may optimize performance, but natural laws continue to define boundaries. Your mind rests in the calm clarity that these challenges are not hypothetical. They are measurable, predictable, and well understood. The rules of motion, energy, and mass provide both guidance and limits, creating a consistent framework for planning and understanding. And as you consider the delicate balance between thrust, mass, energy, and time, your awareness begins to sense that beyond propulsion, the universe itself presents hazards that interact with these challenges. Cosmic radiation, micrometeoroids, and the emptiness of space impose additional constraints, shaping the journey and the limits of what can safely travel among the stars. You begin by noticing that space is not simply empty, but filled with particles and radiation that travel across vast distances. Cosmic rays, originating from exploding stars, pulsars, and other energetic events, move at nearly the speed of light. These high-energy protons and atomic nuclei bombard everything they encounter. You imagine their paths crossing a spacecraft or your own body if you were traveling beyond Earth's protective atmosphere. Each particle carries enormous energy, enough to ionize atoms and damage molecular structures. This invisible hazard pervades the universe, quiet but relentless. The The sun also contributes radiation in the form of solar wind, a continuous stream of charged particles. You consider how this wind interacts with planetary magnetic fields, creating auroras and protecting the surface from the full force of energetic particles. Beyond the heliosphere, however, there is no magnetic shield, leaving travelers fully exposed to cosmic rays and interstellar particles. Observations from spacecraft like Voyager 1 confirm the presence of these high-energy particles in deep space. The numbers are precise and measurable, providing a foundation for understanding the risks involved. You imagine a spacecraft moving at significant fractions of light speed. At such velocities, even a tiny particle in interstellar space can release enormous energy upon impact. Micrometeoroids, though microscopic, collide with kinetic energies far greater than any terrestrial bullet. Spacecraft require shielding designed to absorb or deflect this energy. Engineers use layered materials and Whipple shields, which disperse energy over multiple layers to prevent catastrophic damage. The effectiveness of these designs is confirmed through experimental testing and data from past missions. You follow this reasoning gently, appreciating the quiet ingenuity required to survive the environment. Radiation affects more than just spacecraft structure. High-energy particles can disrupt electronics, erasing memory or inducing malfunctions. You visualize the careful design of circuits and redundancy in critical systems, ensuring that a single cosmic ray does not disable navigation or communication. Observations from satellites in Earth orbit show the effectiveness of shielding and error correction, yet the deeper into space, the greater the risk. You sense a calm respect for the precision of both cosmic hazards and human engineering responses. Humans themselves are vulnerable. Extended exposure to cosmic rays can increase the risk of cancer, damage the nervous system, and affect the cardiovascular system. Research from astronauts aboard the International Space Station and studies of high-altitude pilots provide data on radiation doses and biological effects. Beyond low Earth orbit, shielding is limited, and cumulative exposure over years would become significant. You consider these measured effects carefully, feeling the quiet importance of understanding real physical risks, not hypothetical ones. Interstellar travel also involves prolonged exposure to microgravity, though it is less directly dangerous than radiation. Muscle atrophy and bone density loss occur without consistent gravitational load. Experiments with long-duration astronauts show measurable declines, which can be mitigated by exercise and mechanical stimulation. While not a form of environmental destruction, these effects interact with the hazards of space travel, emphasizing that life beyond Earth requires careful management of both radiation and physiological health. You notice how each factor compounds others, forming a complex but understandable system of challenges. Magnetic fields and plasma from stars and galaxies also create subtle hazards. Charged particles spiral along magnetic field lines, sometimes concentrating in regions called cosmic rays belts. Interstellar magnetic turbulence can deflect charged particles, reducing risk in some directions while increasing it in others. Observations from missions studying cosmic magnetic fields, such as the Parker Solar Probe, provide quantitative data about particle flux and energy levels. You allow this calm, precise information to settle, understanding that space is structured by both forces and hazards in ways that are measurable and predictable. Shielding spacecraft presents engineering trade-offs. Adding mass improves protection, but increased mass requires more fuel and energy for propulsion. Designers must balance safety, efficiency, and speed. Calculations are exact and based on laboratory measurements of material properties, radiation penetration, and particle interaction. You sense the quiet certainty that every design choice has consequences dictated by physics, and that the challenges of travel are cumulative and measurable, rather than vague or speculative. Each factor reinforces the understanding of space as an environment both immense and exacting. You also notice that radiation exposure varies with location. Traveling near stars or in regions of recent supernovae increases particle flux. Even in relatively empty interstellar regions, exposure accumulates over time. Space agencies rely on predictive models, informed by observations, to estimate cumulative doses for astronauts. These models allow mission planners to calculate risk with remarkable accuracy, providing reassurance that, While hazards exist, they are not unknowable. You follow these details calmly, appreciating that careful observation and modeling allow humans to engage with extreme environments responsibly. Dust grains, though minuscule, present additional challenges. At high speeds, impacts can erode surfaces or puncture delicate structures. Observations of interstellar dust show that grains are unevenly distributed, varying in size and composition. Shielding and trajectory planning account for these variations, ensuring that a spacecraft can survive long-duration travel without catastrophic damage. You visualize the microscopic grains, moving silently across the void, and the precision engineering that allows vessels to navigate safely among them. The interplay between cosmic particles and human design is exact and predictable. Space weather influenced by solar activity also has consequences. Solar flares and coronal mass ejections increase particle flux and emit high-energy photons. Satellites in orbit provide real-time observations, allowing warnings and protective measures. Beyond the sun's influence, similar phenomena from distant stars can affect interstellar missions, though their impact is diluted over vast distances. The predictability of these events, combined with shielding, demonstrates that cosmic hazards are not random chaos but structured phenomena governed by physical laws. Your mind rests in the calm certainty of these relationships. Understanding these hazards requires careful measurement and observation. Instruments aboard Voyager, Cassini, and other deep space missions have recorded particle energies, flux, and interactions with spacecraft. Laboratory experiments simulate the effects of radiation on electronics and biological tissue. Data is collected over years, analyzed rigorously, and used to design future missions. You follow the methodical nature of this work gently, sensing the quiet rhythm of observation, verification, and application that underpins safe exploration of interstellar space. You notice that the combination of high-energy particles, micrometeoroids, and radiation creates an environment that is exacting but comprehensible. Each hazard can be quantified, predicted, and mitigated to some extent, yet the sheer scale of exposure over interstellar distances makes these challenges formidable. The universe is not hostile in intention, but it imposes limits and requires careful planning. Your mind absorbs this calm knowledge, understanding that safety and survival in space are matters of physics and preparation, not luck or imagination. And as you rest in this awareness, your thoughts begin to touch on the limits of human endurance. Radiation, particle impacts, and extended exposure to microgravity all interact with the fundamental constraints of life itself, gently guiding your mind toward the consideration of time, lifespan, and the biological challenges of traveling between the stars. You begin by considering the concept of time itself, as experienced on Earth and as measured in the universe. Time is familiar to you through daily cycles, clocks, and seasons. Yet when contemplating interstellar travel, time expands in significance. Distances measured in light years translate into decades or centuries for any traveler moving below the speed of light. Even the closest star, Proxima Centauri, lies over 4 light-years away, at speeds achievable with current or near-future technology. Reaching it would take tens of thousands of years. You notice the quiet magnitude of these durations, letting your mind settle in the calm logic of numbers and physical limits. Special relativity introduces another dimension to time. When an object moves at significant fractions of light speed, time slows relative to stationary observers. This phenomenon, called time dilation, has been measured with atomic clocks on high-speed aircraft and satellites. For a spacecraft approaching light speed, decades for those aboard may correspond to centuries for those remaining on Earth. You imagine observing a clock on the spacecraft and comparing it to one on Earth, seeing the difference gradually accumulate. The concept is precise, predictable, and measurable, and you absorb it gently without needing imagination beyond what physics provides. Even with relativistic time effects, human lifespans impose a practical limit on interstellar travel. Average life expectancy ranges from 70 to 80 years on Earth, although some individuals surpass this. For journeys that span decades, biological limitations make single lifespan travel to even nearby stars improbable. You reflect calmly on this reality, understanding that time itself imposes constraints as tangible as distance or energy. The steady certainty of these limitations creates a framework in which travel and life are both grounded in measurable physics. Generational ships are often proposed as a solution. These are self-sustaining spacecraft where multiple human generations live and die during the journey. Life support, food production, and social structure would need to function continuously for decades or centuries. You imagine carefully designed systems, recycling air and water, growing food, and maintaining health. Even with advanced engineering, these challenges remain formidable. The energy, materials, and planning required multiply with each generation, highlighting that the human factor adds a layer of complexity beyond propulsion and distance. Suspended animation, cryogenic preservation, or other biological technologies have been suggested to extend human lifespans for long voyages. You observe that these concepts are mostly experimental and unproven for multi-decade or century-long durations. The metabolic, neurological, and molecular challenges of keeping humans in stasis are immense. Laboratory studies of hibernation and cryopreservation provide some insight, but the scaling to full human preservation over decades has yet to be demonstrated. You note these limits calmly, recognizing that physics, biology, and engineering all intersect in shaping feasible travel. Time also interacts with planning and communication. Even with instantaneous decisions aboard a spacecraft, news from Earth travels at the speed of light. A message sent from a distant star system would take years to arrive, meaning that travelers are effectively isolated in time as well as space. You consider the practical and psychological consequences of this delay. Every decision, every observation, exists in a context measured in light years and years of travel time. Your mind settles into the awareness of how intimately time constrains all activity beyond our solar system. Relativity also affects mission design. Continuous acceleration could shorten perceived travel time for onboard travelers, but it requires enormous energy and precise engineering. Deceleration at the destination adds additional constraints. You imagine decades of careful operation, where errors accumulate slowly but inevitably. The calculations are exact and predictable, reinforcing the certainty that motion and time are linked through well-understood physical laws. There is no need for speculation. The numbers alone define the reality of interstellar travel. Biological constraints extend to reproduction, aging, and social cohesion. Multi-generational missions must ensure that populations remain healthy and genetically diverse. Life cycles, nutrition, and disease management must be maintained precisely. Research from Earth-based studies of isolated populations, long-duration spaceflight, and small ecosystems informs these considerations. Each human limitation interacts with physical laws, forming a structured system of interdependent constraints. You absorb this knowledge with a calm acceptance of the interplay between life and physics. Time also shapes perception. For travelers on a century-long mission, familiar celestial events, seasons, and planetary observations become markers of passing decades. Space itself appears static, yet time continues inexorably. Observations of pulsars, variable stars, and planetary movements provide predictable rhythms across centuries. You follow these rhythms gently, noticing how time's passage is experienced differently depending on velocity, location, and perspective, and yet remains entirely measurable and consistent across the universe. Even when considering robotic missions, time is a critical factor. Automated probes sent to other stars must operate autonomously for decades, with no human intervention. Energy systems, communications, and data collection must function reliably over extreme durations. Observations from long-duration spacecraft like Voyager and Pioneer provide insight into materials durability, electronics longevity, and the management of autonomous systems. These experiences reinforce that time imposes constraints on all travel, whether human or robotic, and that careful planning and observation allow predictable management of these constraints. As you consider time in relation to human lifespan, a quiet awareness emerges. Interstellar distances translate into multi-generational efforts. Any journey to the nearest stars requires careful integration of physics, biology, and engineering. Even with optimistic assumptions, travel is measured not in months or years, but in decades or centuries. You notice the calm certainty of this reality, appreciating that time is not an abstract concept but a quantifiable, governing factor in any potential voyage. Time also interacts with the universe's other limitations. The speed of light defines how quickly travelers can move, energy requirements determine the feasibility of propulsion, and environmental hazards impose constraints on survival. Each factor combines with human lifespan to create a structured, predictable system. Your mind rests in the logic of these limits, sensing a gentle rhythm in the interaction of time, physics, and biology, a rhythm that is entirely observable and measurable. And as your awareness deepens, you notice that the intersection of lifespan and interstellar distances naturally leads to reflections on communication, signaling, and the exchange of information across the cosmos. Messages, whether from Earth or distant probes, also travel at light speed, emphasizing the patience and precision required to interact across the vastness of space. You begin by noticing that all information in the universe travels at a finite speed. Light, radio waves, and other electromagnetic signals move at approximately 299,792 kilometers per second, the maximum speed allowed by nature. This limit affects how quickly messages can cross the immense distances between stars. Even within our solar system, signals to spacecraft such as those orbiting Mars take minutes to arrive, and replies require the same delay. You feel the quiet reality of these constraints, understanding that every observation, command, or report is bound by time and distance. For interstellar distances, these delays grow dramatically. A signal to Proxima Centauri, just over 4 light-years away, takes more than 4 years to reach its destination. A return message requires an equal amount of time, meaning a simple exchange would take over 8 years. You imagine sending data and then waiting decades for confirmation. Each interval is fixed by the laws of physics, and no technological advancement can reduce the travel time of information beyond this speed limit. The numbers are precise, measurable, and immutable, grounding your awareness in calm certainty. Pulsars provide a natural example of communication over vast distances. These rotating neutron stars emit regular pulses of radio waves that travel across the galaxy at light speed. By observing pulsars, astronomers can track time and detect movement with remarkable precision. The information from these signals reaches Earth over hundreds or thousands of years, yet it arrives in an exact, predictable pattern. You follow the rhythm of these pulses in your mind, appreciating the reliability of natural signals as they traverse the void. Each pulse demonstrates the patient logic of cosmic communication. Spacecraft telemetry illustrates human-engineered communication across space. Missions like Voyager, Pioneer, and New Horizons send data back to Earth using radio waves. These signals are faint, requiring large antennas and precise timing to capture. Engineers calculate trajectories and signal travel times with extraordinary accuracy, ensuring that every bit of information is accounted for. Observing this process reveals how physics governs communication, creating delays that are exact and unavoidable. You sense the calm inevitability of these constraints, knowing that even the most advanced technology is limited by the speed of light. The finite speed of communication also influences mission planning. Remote operations must anticipate delays in receiving instructions and transmitting responses. For robotic missions beyond the solar system, control is largely autonomous because real-time input is impossible. You imagine a probe navigating interstellar space, adjusting its course based on local observations, yet unable to receive immediate guidance from Earth. Each adjustment, each calculation, must be self-contained. The interplay between autonomy and communication illustrates the delicate balance required when information cannot travel faster than light. You notice that light speed limits also define the universe's observable structure. Every galaxy, star, and planet you see is seen as it existed in the past, because its light takes years, centuries, or millennia to reach Earth. In a sense, the universe communicates its history to you through the finite travel time of light. You follow this logic gently, observing that every signal, whether natural or artificial, is a record of earlier events, faithfully transmitted across space without distortion. The consistency of these signals provides both knowledge and perspective. The distance-related delay also shapes expectations for interstellar contact. Even with hypothetical intelligent civilizations, any exchange of information would require patience measured in decades or centuries. Messages sent today might not be received for generations, and replies would take equally long. You sense the calm understanding that such constraints are inherent in the cosmos, set by measurable, verifiable physical laws. The universe operates in a rhythm defined by light and electromagnetic propagation, and all communication must respect this rhythm. Signal degradation is another consideration. Over vast distances, electromagnetic waves spread and weaken, requiring sensitive receivers and error-correcting methods. Space agencies design antennas, amplifiers, and coding protocols to ensure that data remains intact despite enormous distances. Observations from deep space networks demonstrate that precise engineering can overcome some practical challenges, but cannot alter the fundamental speed limit. You follow this process slowly, appreciating the careful combination of physics and engineering that allows reliable communication even across light years. You also notice that communication delays shape perception and decision-making. Astronomers observing a distant supernova, for example, see it as it occurred millions of years ago. Any attempt to act or influence the event is impossible. Observation is limited to reception of information already carried by light. Similarly, any interstellar mission cannot receive timely updates from Earth beyond the delay imposed by distance. These constraints are exact, predictable, and governed entirely by the physics of light propagation. Your mind absorbs this certainty with a calm sense of order. Relativistic effects influence communication at high velocities. Time dilation affects onboard clocks relative to Earth, altering the perceived timing of messages. Engineers account for these differences in deep space missions, adjusting signal timing and synchronization to ensure that information remains meaningful. These corrections rely on established equations from special relativity, confirming that the universe's rules are consistent, measurable, and manageable. You feel a quiet reassurance in the predictability of these relationships. You reflect on the combination of distance, light speed limits, and technological constraints. Sending a message across even a few light years is not merely a matter of energy or power. It is constrained by immutable cosmic law. Whether for human travelers, robotic probes, or distant observation, these boundaries define what is possible. You notice the gentle precision of these limits, and how they create a structured, measurable framework for all communication in the universe. Observations of pulsars, quasars, and distant galaxies reinforce the predictability of cosmic signals. Astronomers rely on these natural beacons to calibrate instruments, track time, and study cosmic phenomena. Each observation confirms that light carries information faithfully across space, constrained by its constant speed. You imagine following these signals over decades, noting their arrival time and intensity. The regularity of these measurements illustrates a quiet order in the cosmos, reassuring and precise. You also consider the implications for deep space navigation. Spacecraft must plan maneuvers far in advance, accounting for delays in receiving guidance from Earth. Autonomous systems calculate course corrections and adjust propulsion based on real-time observations, but must operate independently due to the lag in information. You imagine the careful balance between autonomy and delayed communication, understanding that the universe enforces strict timing rules. Every adjustment respects the immutable speed of light, integrating physics into practical operations. And as you absorb the limits of light-speed communication, your awareness naturally turns toward the challenges of sustaining hardware and humans across these distances. Just as signals require precise management and careful planning, so too must life and instruments endure the extended journey through space, where distance, energy, and the environment all converge to shape what is possible. You begin by observing that all objects, from spacecraft to instruments, are constrained by the properties of the materials from which they are built. Even the most advanced alloys and composites have limits to strength, flexibility, and durability. In interstellar travel, these constraints become critical. High velocities, constant exposure to radiation, and impacts from micrometeoroids impose stresses that exceed typical Earth-based conditions. You feel a gentle awareness of these limits, recognizing that engineering is grounded in measurable material properties, not imagination or speculation. You consider tensile strength, the maximum force a material can withstand when being stretched. Metals such as titanium and aluminum alloys are strong, but even they deform under extreme acceleration or stress. Composites and ceramics can resist heat and abrasion, yet they are brittle under sudden impacts. Engineers must carefully select materials based on the specific conditions a spacecraft will encounter, balancing strength, weight, and resistance to radiation. Every choice is quantifiable, informed by laboratory tests and decades of observation. High acceleration imposes additional demands. When a spacecraft accelerates steadily toward a significant fraction of light speed, every component experiences increased force. Internal structures, fasteners, and fuel tanks all must withstand this continuous stress. You imagine calculating the stresses along beams and panels, predicting potential points of failure with precision. Finite element analysis and simulations allow engineers to model these forces before construction. The careful measurement of each effect provides confidence that the spacecraft will remain intact during long-duration acceleration. Radiation interacts with materials in specific ways. High-energy cosmic rays can displace atoms, weaken structural bonds, and alter electrical properties. Shielding, whether aluminum, lead, or specialized composites, absorbs or deflects much of this energy. You visualize layers of material engineered to scatter radiation and prevent damage to sensitive electronics or crew compartments. Observations from spacecraft exposed to radiation over years, including satellites in Earth orbit, provide empirical confirmation of material performance. Each measurement is precise, giving engineers confidence in their designs. Micrometeoroid impacts present another constraint. At high velocities, even particles smaller than a grain of sand carry enormous kinetic energy. Impacts can puncture hulls, erode surfaces, or damage instruments. Engineers use Whipple shields, consisting of multiple layers separated by space, to dissipate impact energy gradually. Laboratory testing simulates these collisions, measuring penetration depth and structural response. You follow the slow, meticulous logic of these designs, appreciating the way physics dictates the exact configuration of protective materials. Thermal expansion is also a concern. Spacecraft moving between regions of high radiation exposure and deep interstellar cold experience temperature variations that cause materials to expand and contract. Metals expand predictably with heat, and composites behave differently. Engineers account for these variations in structural design and mounting of sensitive components. You imagine carefully calculating tolerances, leaving precise gaps or flexible joints that accommodate thermal shifts without failure. The balance of materials and environment is exact, governed by measurable properties and predictable physics. Electrical systems are constrained by material limits as well. Wiring, semiconductors, and energy storage devices degrade over time and with exposure to radiation. Insulating materials can break down, batteries lose efficiency, and electronic circuits can experience bit flips due to high-energy particles. Observations from satellites and probes confirm these effects, and engineers incorporate redundancy, shielding, and error-correcting codes to ensure reliable operation. Every choice is supported by experimental data and precise measurement. Mass considerations intersect with material properties. Stronger materials are often denser, adding weight and requiring more energy for acceleration. Lightweight materials reduce propulsion demands but may be more brittle or less resistant to radiation. Engineers model the trade-offs, calculating optimal configurations that balance strength, protection, and energy efficiency. These calculations are exact, based on the laws of physics, material databases, and laboratory measurements. You feel the gentle precision of this optimization process. Long-duration missions introduce aging and fatigue. Metals develop microcracks, composites experience delamination, and polymers degrade under radiation and temperature fluctuations. Engineers simulate these effects with accelerated testing, extrapolating performance over decades. Predictive modeling ensures that materials retain integrity over the mission lifetime. You notice how careful measurement and planning allow reliable prediction of material behavior, turning potential hazards into quantifiable, manageable challenges. Propulsion systems also impose engineering realities. Engines must withstand heat, vibration, and chemical or nuclear reactions. Fuel tanks must resist pressure fluctuations, and moving parts must operate reliably for decades. Laboratory tests, simulations, and historical spacecraft performance inform these designs. Every component interacts with others in a precise, measured way, forming a system constrained by the limits of materials and physical law. Your mind absorbs this reality calmly, appreciating the careful orchestration required to maintain functionality over vast distances. You also consider repair and redundancy. No system is perfect, and over decades, components can fail. Engineers design spacecraft with modular systems, backup circuits, and multiple pathways for critical functions. Observations of long-duration probes, such as Voyager, confirm that redundancy increases reliability over time. You imagine each subsystem carefully duplicated, monitored, and maintained, guided entirely by physics and engineering principles. The universe imposes constraints, and human design responds predictably. Shielding against radiation and impacts introduces another interplay with mass and structure. Thick protective layers absorb energy but add weight, increasing propulsion demands. Engineers must balance thickness, density, and composition to optimize protection while conserving fuel. Simulations and experiments measure penetration depths, scattering angles, and energy absorption. Every choice is grounded in observation and calculation, creating a calm, precise understanding of the trade-offs involved. The chemical and thermal stability of materials is also critical. Components exposed to energetic particles, temperature extremes, or reactive fuels must maintain chemical integrity. Laboratory measurements provide precise data on degradation rates, thermal conductivity, and reactivity. Engineers integrate these numbers into design, ensuring materials remain stable for decades or centuries. You follow the meticulous logic of these selections, noticing how predictable physical behavior allows long-term planning in an otherwise extreme environment. And as you rest in the understanding of these material and engineering limits, your awareness gently turns toward the broader implications. The durability of spacecraft, the resilience of structures, and the careful management of energy and mass all form the foundation for interstellar journeys. These constraints, measured and predictable, prepare your mind to consider the next challenge: the immense distances between stars and the scale of planning required to traverse them. You begin by considering the enormous resources needed to send even a small spacecraft to another star. Every aspect of the mission, from energy to materials, must be scaled to a level far beyond anything humanity has undertaken. Current space missions, like those to Mars or the outer planets, already consume vast quantities of fuel, materials, and funding. You notice how each kilogram of mass increases energy requirements exponentially, and you let the calm certainty of these numbers settle. The universe sets the scale, and physics quantifies what is necessary to move matter across light years. Energy is the first major constraint. Chemical rockets, nuclear engines, or theoretical antimatter propulsion all require tremendous quantities of energy. You imagine the calculation. Accelerating a spacecraft to a fraction of light speed consumes energy comparable to the annual output of an entire nation, even for modest payloads. Expanding this to a multi-ton vessel for human travel increases the requirement by orders of magnitude. Observational data from terrestrial energy consumption, power plants, and space missions confirms these calculations. Each figure is precise, measurable, and anchored in reality. Materials present another significant constraint. Metals, composites, and shielding layers must be produced in unprecedented quantities. Even lightweight materials add mass that must be accelerated, multiplying energy costs. You follow the logistics of mining, refining, and transporting raw materials, and you notice the scale of industrial infrastructure required. Current production rates for high-performance alloys are insufficient for a single interstellar mission, let alone sustained efforts. Your mind absorbs this calmly, understanding that resources are a physical limitation, not merely a matter of funding. The scale of manufacturing also involves labor, knowledge, and precision engineering. Spacecraft components must meet exacting tolerances to function over decades or centuries. Every system, from propulsion to life support, must be constructed with reliability verified through extensive testing. Observational evidence from long-duration missions, like Voyager, shows that even small errors can accumulate over time, highlighting the importance of meticulous construction. You feel a quiet understanding that interstellar missions demand resources in both materials and human expertise on a level far exceeding contemporary practice. Fuel and energy storage create further logistical challenges. Nuclear and antimatter propulsion require controlled, high-density energy sources. Producing, transporting, and safely storing these fuels requires infrastructure orders of magnitude beyond current capabilities. Each kilogram must be handled with extreme care to prevent accidents. Observational data from laboratory experiments and reactor operations provides insight into what is technically possible, but the scale required for interstellar travel exceeds what any nation or coalition can currently supply. You follow the logic of these calculations slowly, absorbing their significance. Costs also scale exponentially with mass and distance. The more massive a spacecraft, the more energy is required, which in turn increases fuel requirements and total launch mass. Observational data from rocket launches shows that even launching small payloads is expensive. Multiply this for interstellar-scale missions, and the financial requirements approach the combined economic output of entire civilizations over years or decades. Your mind rests in the calm certainty that these figures are not speculative. They are grounded in measurable energy, materials, and distance. Infrastructure beyond the spacecraft itself is equally critical. Launch facilities, communication networks, and monitoring stations must operate continuously for decades. You imagine a global network coordinating resources, tracking propulsion, and maintaining life support systems. Observations from space agencies show that even small lapses in infrastructure can compromise complex missions. For interstellar endeavors, continuity must be maintained over generational timescales. Your awareness absorbs the precision of these requirements, recognizing that logistical planning is as much a constraint as physics. You also consider sustainability and long-term support. A multi-decade or multi-century mission would require reliable supply chains for replacement parts, energy, and possibly crew support. Earth's current industrial output is orders of magnitude too small to meet these demands. Even robotic probes of modest mass far exceed existing production capacity when scaled for interstellar travel. Observational and experimental evidence from large-scale engineering projects, such as international fusion research or satellite constellations, provides insight into these challenges. You notice the calm inevitability of resource limitations. Economics also interacts with physics. The energy required, the materials consumed, and the engineering precision needed all translate directly into cost. Observations of past space programs, from Apollo to the International Space Station, provide real benchmarks. Even modest interplanetary missions have consumed billions of dollars. Scaling these costs for interstellar travel reaches a magnitude that current economic structures cannot support. Your mind rests in the clarity that interstellar missions are bounded not only by energy and materials but by measurable, real-world economic capacity. You also reflect on global cooperation. A project of interstellar scale would likely require collaboration across nations, combining technological capabilities, energy resources, and industrial infrastructure. Observational data from multinational space projects confirms the complexity of coordination even on smaller scales. Scaling this to interstellar requirements introduces challenges in governance, resource allocation, and long-term political stability. You sense the calm logic of these realities, understanding that human organization interacts directly with physical and technological constraints. Transporting materials from Earth to space adds further scale challenges. Launch costs are energy-intensive and currently extremely expensive per kilogram. Observational data from reusable rockets and planned space elevators suggest some improvements are possible, but the fundamental limits of orbital mechanics, propulsion, and mass remain. Every kilogram must be accounted for, and any reduction in mass translates to significant energy savings. You follow these calculations slowly, letting the rhythm of logistics and physics settle into a measured understanding. You notice that even theoretical solutions, like self-replicating machines or in-situ resource utilization, face scaling challenges. Mining asteroids, constructing components in space, and producing fuel off-planet are possible in principle but require decades of infrastructure buildup. Observations of asteroid composition, orbital mechanics, and mining simulations provide guidance, but the scale of effort is immense. The universe imposes exact physical constraints, and economics, engineering, and human organization must work within them. Your mind absorbs the precision of these combined limits. Ultimately, you realize that interstellar travel is not impossible, but it is far beyond current human capability. Physics, energy, materials, and infrastructure define exact boundaries. Economics and logistics add additional measurable constraints, demonstrating that the challenge is as much societal as technological. You sense a calm acceptance that these limits are not arbitrary but grounded in quantifiable reality. The universe provides a clear framework, and understanding it allows the mind to appreciate both ambition and feasibility. And as you rest in the awareness of the vast scale of resources required, your attention naturally begins to move toward the human element, the biology, psychology, and endurance of those who might travel among the stars, where life itself becomes a critical factor in the equation. You begin by observing how humans are adapted to life on Earth, where gravity, atmospheric pressure, and a magnetic field provide stable conditions. In space, these conditions are absent or altered, creating challenges that affect both body and mind. Microgravity, for example, causes the body to adjust in ways that are measurable and predictable. Muscles used to supporting weight begin to weaken, bones lose density, and the cardiovascular system adapts to the reduced load. You follow these changes slowly, noticing the precise physiological responses, and feel a gentle awareness of how finely tuned human biology is to Earth. Muscle atrophy is among the most significant effects. Research on astronauts aboard the International Space Station shows measurable declines in muscle mass and strength, particularly in the lower body and back. Exercise protocols mitigate these effects, but cannot fully replicate the constant resistance of Earth's gravity. You imagine the long-term consequences for someone traveling for decades in space, understanding that without continuous intervention, physical ability would decline. The observations are exact, based on data, and they reinforce the necessity of careful planning for prolonged missions. Bone density loss occurs alongside muscle atrophy. In microgravity, bones do not experience the stress required to maintain their structure. Calcium is released into the bloodstream, increasing the risk of kidney stones and reducing skeletal strength. Observational studies quantify these changes, showing declines of several % per month in weight-bearing bones. You notice the calm precision of these numbers, appreciating that biology responds predictably to environmental changes. Planning for interstellar travel must address these physiological realities to ensure survival and long-term health. Radiation exposure compounds these biological challenges. Cosmic rays and solar energetic particles penetrate shielding and can damage DNA, increasing the risk of cancer and other disorders. Observations from astronauts and high-altitude pilots allow measurement of doses and their effects. Shielding, careful mission timing, and protective strategies reduce exposure but cannot eliminate it entirely. You follow the logic of these interactions, understanding that radiation is a constant, quantifiable hazard that imposes limits on human presence in space. Microgravity also affects fluid distribution in the body. Blood and other fluids shift toward the head, altering vision, pressure regulation, and cardiovascular function. Observations from long-duration missions show measurable changes in intracranial pressure and ocular health. These effects are gradual but significant over months or years. You notice the quiet consistency of these biological responses, governed by physical principles, and you absorb the calm certainty that understanding them allows for mitigation and planning. Cognitive and psychological factors are equally important. Isolation, confinement, and sensory monotony influence mood, attention, and decision-making. Observational studies of space missions and Antarctic research stations provide quantitative data on stress, sleep disruption, and social dynamics. You imagine a crew spending years in enclosed spaces with limited social interaction and external stimuli. The science shows measurable changes in cognitive performance and emotional stability. You sense a quiet acceptance that human behavior in extreme environments is a factor as concrete as radiation or microgravity. Sleep is affected by the absence of natural day-night cycles. Astronauts rely on artificial lighting to maintain circadian rhythms, but disruptions are measurable and can influence alertness, memory, and health. You follow the gradual adjustments of the body, noting that even small deviations accumulate over months or years. These patterns are predictable, allowing interventions such as lighting schedules and controlled rest periods. Observational evidence confirms that managing sleep is essential for long-duration missions, reinforcing the interplay between physiology and mission planning. Nutrition and metabolism also interact with the challenges of space. Reduced physical activity, altered digestion, and radiation exposure influence nutrient requirements. Observational studies inform precise formulations for food design to maintain health over extended periods. You imagine careful monitoring of intake, hydration, and caloric balance, understanding that small deviations can accumulate over decades. Biology interacts with engineering in predictable ways, and planning can mitigate many risks if grounded in evidence-based research. Immune system function changes in space. Studies show alterations in white blood cell activity, inflammatory responses, and pathogen resistance. Observations indicate that long-duration missions require careful monitoring, vaccination, and medical preparedness. Even minor infections can become significant if left untreated in an isolated environment. You follow the logic calmly, noting that human physiology responds to extreme environments with measurable patterns, and that understanding these patterns allows for planning and risk reduction. Radiation and microgravity together compound challenges for reproduction, growth, and development. Animal studies demonstrate measurable effects on fertility, embryonic development, and cellular division under conditions of altered gravity and radiation exposure. While human reproduction in space remains largely theoretical, these studies highlight constraints grounded in biology and physics. You absorb the steady, measurable evidence, noticing the precise ways in which fundamental life processes are influenced by environment and distance from Earth. The psychological impact of prolonged travel is amplified by distance and isolation. Astronauts report feelings of monotony, anxiety, and sensory deprivation, even on missions lasting months. Studies quantify changes in attention, problem-solving, and interpersonal dynamics. You imagine multi-decade voyages, understanding that social cohesion, mental health support, and structured activity are essential for maintaining function. Observation and research show these effects are predictable, measurable, and addressable with careful design. Finally, all these biological and psychological challenges are interconnected. Muscle and bone loss influence mobility, which affects daily tasks and exercise routines. Radiation impacts cellular function, which interacts with immune responses and long-term health. Psychological stress influences behavior and decision-making, which in turn affects mission safety and performance. Observational studies confirm these interactions are systematic and predictable. You follow this network of relationships slowly, noticing the quiet precision of how biology and physics intersect in space travel. And as you rest in the awareness of these combined human challenges, your mind gently turns toward potential solutions, robotic support, multi-generational planning, and technologies designed to extend life and capability, while remaining firmly grounded in measurable science and observable reality. You begin by considering robotic probes as a way to explore interstellar space without exposing humans to extreme risks. Probes like Voyager, New Horizons, and Cassini have traveled vast distances, sending back precise data about planets, moons, and the outer solar system. These missions demonstrate that machines can survive harsh environments for decades with careful design, redundancy, and robust engineering. Observations show that instruments degrade slowly over time, yet data transmission continues. You follow these lessons, noticing that robotic exploration is bounded by measurable constraints, such as power, communications delay, and radiation exposure. Energy supply is a critical limit for robotic systems. Solar panels work well near stars but become less effective in deep interstellar space. Radioisotope thermoelectric generators provide long-term power but are limited in energy output. Engineers must carefully balance energy budgets for propulsion, data collection, and communication. Observational data from spacecraft confirms that power shortages can halt operations, even when all other systems function correctly. You notice the precise, predictable interplay between energy production and mission longevity, understanding that these limits are grounded in physics and observable reality. Autonomy is essential for robotic missions across light years. The finite speed of light prevents real-time control from Earth. Probes must make navigation, data collection, and anomaly responses independently. You imagine artificial intelligence systems executing precise, pre-programmed instructions, adjusting to unpredicted conditions with onboard sensors. Observations from autonomous rovers on Mars show that decision-making can be effective when algorithms are carefully tested. Even so, unanticipated events remain a challenge, emphasizing that robotics mitigates human risk but cannot overcome all constraints imposed by distance and time. Generational ships represent a different approach. These hypothetical spacecraft would carry human populations over multiple generations, maintaining life, culture, and continuity across decades or centuries. Observational studies of long-duration habitation in isolated environments, such as Antarctic stations or submarines, provide insight into the dynamics of confined populations. Maintaining social cohesion, governance, and health over generations is measurable and requires structured planning. You sense the calm inevitability that population management and life support are as critical as propulsion and materials, forming a network of predictable challenges. Life support on generational ships must be nearly self-sustaining. Air, water, and food cycles need to operate continuously, relying on recycling systems, hydroponics, and closed-loop ecological models. Observational data from long-duration space habitats show that even minor inefficiencies can accumulate, affecting resource availability. Engineers model growth rates, nutrient cycling, and waste management with measurable precision. You follow this logic gently, noting that while technology can sustain life, limits remain defined by materials, energy, and biological processes. Suspended animation and cryogenic preservation have been proposed as methods to extend human lifespan and reduce resource consumption during interstellar travel. Laboratory experiments in animal hibernation, low-temperature metabolism reduction, and induced torpor provide insight into the possibilities. You imagine controlled metabolic suppression allowing decades of stasis. Observational data, however, shows significant challenges. Long-term preservation of cellular integrity, avoidance of ice crystal formation, and maintenance of neurological function remain unresolved for humans. These limits are measurable, grounded in biology and physics, and define the boundaries of feasibility. Robotic precursors to human missions can reduce risk, yet they cannot fully replicate human observation and decision-making. Probes collect data, but humans interpret nuance, context, and unforeseen phenomena. Observational evidence confirms that even with advanced AI, autonomous systems are constrained by programming and sensor limitations. You notice that interstellar exploration, when bounded by physical and technological limits, becomes a matter of carefully allocating human presence, robotic support, and autonomous decision-making in a complementary system. Time and distance remain fundamental constraints for all approaches. Even with optimal propulsion, travel to the nearest star spans decades. Communication delays, energy requirements, and exposure to space hazards compound the challenge. Observational studies of deep space missions and theoretical calculations of relativistic effects provide precise measures of duration and resource needs. You follow the steady logic, appreciating that creativity in planning is bounded by exact, quantifiable physical laws. Ethical considerations also define practical limits. Multi-generational missions require careful planning of governance, social structure, and genetic diversity. Observations of small, isolated communities on Earth provide measurable data on population stability, reproductive health, and societal cohesion. Planning for centuries of continuous human life in confined conditions cannot ignore predictable psychological and social dynamics. You sense the calm certainty that human presence is constrained not only by physics and engineering but by measurable social and biological factors. Even the most imaginative approaches, such as light sails or fusion-powered ships, face tangible limitations. Acceleration is constrained by energy availability, while structural materials must resist stress over decades. Radiation and micrometeoroid exposure create cumulative damage. Observational studies of particle flux, material science, and propulsion systems provide precise parameters for what is achievable. You follow these calculations slowly, noting that all creativity is anchored by the immutable laws of physics, energy, and material science. Redundancy, repair, and maintenance are additional constraints. Multi-generational or long-duration robotic systems must anticipate component failure over decades. Observations from deep space probes and experiments in long-duration habitations show predictable rates of material fatigue, electronic failure, and system degradation. Engineers plan for modular replacements, repair protocols, and autonomous troubleshooting. You absorb this reasoning calmly, appreciating that reliability is quantifiable and that contingency planning is a necessary, measurable component of any interstellar mission. Scaling resources is another critical factor. Generational ships and large autonomous systems require energy, materials, and logistics far beyond anything humanity currently produces. Observational data from industrial production and energy use confirms that the scale is not merely a technological challenge, but a societal one. Energy production, material extraction, and infrastructure must operate continuously for decades or centuries. You notice the precise interactions between resource availability and mission feasibility, allowing your mind to rest in the calm order of numbers and limits. Ultimately, every alternative approach, robotic, generational, or suspended animation, is bounded by measurable constraints. Physics defines speed, energy, and material limits. Biology sets endurance, metabolism, and lifespan boundaries. Engineering dictates the feasibility of systems, redundancy, and resilience. Economics and logistics define what scale of resources is available. Observations, experiments, and simulations provide exact numbers for each factor. Your mind absorbs the clarity that creativity operates within these tangible limits, forming a structured understanding of what is feasible and what remains speculative. And as you rest in the awareness of these alternative approaches, your attention turns toward what can realistically be achieved today and within the solar system. While interstellar travel faces extreme constraints, nearby exploration, observation, and robotic missions provide meaningful and measurable opportunities, grounded in physics, biology, and engineering. You begin by observing the solar system, noting its vast yet accessible scale. Planets, moons, and smaller bodies orbit the sun in predictable paths. Spacecraft launched from Earth can reach Mars in months, the outer planets in years, and some comets and asteroids in weeks or months. The distances, though immense compared to everyday scales, are measurable and navigable using known physics and current technology. Your mind rests in the calm understanding that these journeys are within human capability, bounded by precise laws and careful engineering. Robotic exploration provides a particularly effective way to study these nearby targets. Missions like Mars rovers, Juno at Jupiter, and Cassini at Saturn demonstrate the capacity to explore, analyze, and report detailed information over years. Instruments measure atmospheric composition, surface geology, magnetic fields, and radiation levels with exact precision. Observations are transmitted to Earth, delayed by minutes to hours, but remain fully interpretable. You notice how robotic systems allow sustained scientific work without exposing humans to the harshest hazards of space, and you follow this logic with quiet appreciation. Satellites and telescopes expand human observation beyond the immediate solar system. Instruments like Hubble, Kepler, and the James Webb Space Telescope detect exoplanets, stellar spectra, and distant galaxies. Observational data from these instruments reveal patterns of star formation, planetary distribution, and cosmic evolution. You imagine following the light captured by these telescopes, traveling across years and light years, arriving at precise sensors designed to measure every photon. The information they provide allows profound understanding without physical presence, demonstrating the power of remote observation. Asteroid and comet missions illustrate practical exploration on smaller scales. Spacecraft like OSIRIS-RX and Hayabusa 2 navigate and sample bodies smaller than many cities. Observational measurements confirm their composition, density, and structure, providing insight into the formation of the solar system. These missions demonstrate that even relatively tiny objects can be approached, measured, and sampled with high precision. You follow the careful logic of trajectory planning, instrumentation, and surface interaction, feeling the calm reassurance of predictable outcomes. Planetary landers and orbiters allow detailed study of atmospheres, geology, and potential habitability. Mars missions provide evidence of water flow, ice deposits, and past volcanic activity. Observations are verified over multiple missions, showing consistency in measurement and interpretation. You imagine observing these landscapes, analyzing chemical signatures, and interpreting geological history, all from instruments operating remotely. Each data point is precise, measurable, and confirms what is possible within reachable distances. Space-based solar system observation also enhances safety and navigation. Tracking near-Earth objects, monitoring solar activity, and predicting orbital dynamics are all essential tasks. Observational data inform trajectory corrections, collision avoidance, and energy management for spacecraft. Each prediction is grounded in measurable physics, orbital mechanics, and material properties. You follow this logic slowly, sensing the reliability of science in supporting both exploration and protection of Earth-based infrastructure. Human presence in low Earth orbit demonstrates manageable long-duration exploration. The International Space Station shows that life can be sustained for months to years in microgravity, with predictable effects on biology, materials, and energy systems. Observations provide clear, quantitative measurements of muscle atrophy, bone density loss, and radiation exposure. These findings allow incremental improvement in life support, exercise regimens, and shielding. You notice the calm precision in which these experiments inform the design of future missions, creating confidence in what humans can safely achieve nearby. The Moon represents another reachable milestone. Observational and landing missions provide exact maps of terrain, composition, and environmental conditions. Robotic landers confirm surface properties, while future missions aim to establish sustainable habitats. Energy requirements, radiation exposure, and logistics remain measurable challenges, yet all are solvable with existing technology. You imagine walking across the lunar surface or observing it through detailed data, sensing the satisfaction of exploration that is firmly bounded by reality and physics. Mars provides a target for both robotic and eventual human exploration. Travel requires careful energy calculations, life support, and radiation shielding, all grounded in measured science. Missions observe seasonal changes, ice deposits, and atmospheric composition. Each measurement is precise, forming a foundation for understanding how humans might survive and operate there. You notice the calm logic in these endeavors. Science guides each step, providing measurable results and predictable outcomes. Exploring the outer planets with orbiters and probes also provides measurable insight. Jupiter's radiation belts, Saturn's rings, and the icy moons offer scientific richness that can be accessed and measured remotely. Spacecraft like Galileo and Cassini provide continuous, high-precision data over years. Observations reveal magnetic fields, geological activity, and chemical composition. You follow the gradual accumulation of knowledge, sensing the satisfaction of learning within the bounds of reachable distances. Even exoplanet studies illustrate achievable goals. Light curves, spectra, and orbital analysis allow measurement of planetary size, composition, and distance. You notice that even without traveling to these stars, observation yields profound understanding. Observations are grounded in measurable physics and precise instruments, allowing study across vast distances. You follow the exact numbers, light years, and orbital calculations, feeling a calm sense of curiosity satisfied by real science. And as you rest in the awareness of what is possible within the solar system and nearby space, your mind naturally appreciates the combination of achievable exploration, robotic precision, and human ingenuity. The universe is vast, yet within reach, measurable, and navigable, allowing deep understanding without leaving the bounds of safety and evidence-based practice. You notice that each observation, calculation, and mission creates a foundation of certainty, reinforcing the quiet satisfaction of knowledge gained within reach. You begin by observing the vast structures of the universe, knowing that every star, galaxy, and cluster follows precise physical laws. Galaxies rotate, stars shine, and cosmic filaments trace patterns of gravity and matter across enormous distances. Observational astronomy provides clear evidence of these patterns, using measurements of light, spectra, and motion. You notice the exact regularity in these structures, sensing a calm satisfaction in understanding how physics organizes the cosmos with precision and predictability. The life cycles of stars are particularly observable and measurable. Hydrogen fuses into helium, producing energy that sustains stellar luminosity. Over millions to billions of years, stars evolve, expanding into red giants or collapsing into white dwarfs, neutron stars, or black holes. Observations confirm these stages through spectroscopy, brightness measurements, and gravitational interactions. You follow this logic slowly, noting that even the most dramatic transformations are governed by well-understood physical laws. Each star operates within a framework that is predictable and measurable. Galaxies themselves are also dynamic yet bounded systems. Spiral arms, elliptical distributions, and clusters form according to gravitational dynamics, dark matter distribution, and angular momentum conservation. Observational evidence from telescopes across wavelengths confirms these structures, showing patterns repeated across billions of light-years. You imagine tracing the motion of stars within a galaxy, measuring rotation curves and orbital velocities. These numbers, precise and observable, reveal the calm order underlying cosmic complexity. Interstellar matter, including gas, dust, and cosmic rays, moves through galaxies in measurable ways. Star formation occurs in molecular clouds where density, temperature, and turbulence meet predictable criteria. Observations in radio, infrared, and visible light confirm the locations and rates of star formation. You follow these processes with gentle attention, sensing the predictable rhythms of birth and evolution in the cosmos. Each new star, while unique, conforms to well-established physics, allowing understanding across vast distances and timescales. Black holes demonstrate the limits of observable phenomena. Their gravitational pull is measurable through orbital motions, accretion disk radiation, and gravitational lensing. Observations confirm the masses and behavior of these objects with high precision. You notice the calm certainty in these measurements, understanding that even the most extreme regions of the universe obey predictable laws. Physics provides a framework for understanding, and observations reinforce that knowledge. Clusters of galaxies illustrate large-scale structure. Gravitational interactions bind these systems, while dark matter influences motion and distribution. Observations using X-ray, optical, and radio telescopes quantify mass, velocity, and energy. You imagine following the gentle motion of these clusters, noting how every measurement conforms to general relativity and cosmological models. The universe operates consistently, and each observation confirms the framework within which matter and energy move. Cosmic background radiation provides another precise measure of the universe's structure and history. Observations from instruments like COBE, WMAP, and Planck map minute fluctuations in temperature, revealing the distribution of matter in the early universe. You follow these measurements, noting the regularity and precision in data that informs cosmological models. Even over billions of years, the observable universe adheres to patterns grounded in physics, offering a foundation of certainty for understanding cosmic evolution. Stellar remnants, including white dwarfs, neutron stars, and supernovae, demonstrate the conservation of mass, energy, and angular momentum. Observations quantify luminosity, expansion, and elemental synthesis. Each measurement confirms theoretical predictions, providing exact numbers for energy output, mass, and composition. You follow the slow unfolding of these events, noticing the predictable interplay of nuclear physics, gravity, and thermodynamics. The universe operates according to consistent, measurable principles, and these remnants testify to that reliability. Exoplanets provide a final layer of measurable wonder. Observations reveal planetary size, orbital period, and composition, using transit methods, radial velocity, and direct imaging. Even without traveling to these systems, data provides precise, interpretable information about their nature. You notice the rhythm of orbits, the stability of systems, and the interaction of light and gravity, all measurable and predictable. Your mind absorbs the satisfaction of knowledge obtained at a distance, grounded in physics and observation. Cosmic expansion, measured through redshift and standard candles, illustrates both the scale and the limits of observation. Galaxies recede from one another in a predictable, measurable pattern consistent with general relativity and cosmology. Observational evidence quantifies the expansion rate and informs models of the universe's age, currently estimated at approximately 13 billion years. You follow this slow unfolding with gentle attention, noting that even the largest motions in the cosmos adhere to precise physical laws. You also reflect on the limits of observation. Light takes time to travel, so every object you see is a record of the past. This delay is measurable and predictable, defining the observable universe. The universe beyond a certain distance is inaccessible to direct observation, bounded by the speed of light and cosmic expansion. You notice the calm reassurance in these limits. They are not arbitrary, but clearly defined by physics and observation, creating a structured framework for understanding. Even in the bound universe, there is vastness to explore. Every measurement, from the spectrum of a distant quasar to the orbit of a nearby asteroid, adds certainty to knowledge. Each observation is repeatable and verifiable, grounded in physics. You notice that curiosity and exploration do not require the impossible. The universe offers measurable phenomena that can be studied with precision and confidence. Knowledge grows steadily, predictably, and reliably. And as you rest in the awareness of this vast, bound, and measurable cosmos, your mind settles into the rhythm of observed and predictable processes. Stars shine, galaxies rotate, planets orbit, and light travels steadily through space. Every measurement reinforces the reliability of physical law. You notice that even within limits, there is endless opportunity to observe, understand, and reflect. The universe is large, structured, and knowable, and your mind finds quiet satisfaction in its calm, evidence-based order, gently preparing for a deep and informed rest.